Hey everybody, this is Larry. This is day 19 of the Leetcode Day Challenge. What is this early access stuff? I don't want to try it. Hit the like button, hit the subscribe button, join me on Discord. Let me know what you think about today's problem. 1489, find critical and pseudo-critical edges in minimum spanning tree. It's a hard problem, so hopefully we'll get through it. I've been having, some struggles lately, as people who's been watching my channel know. So yeah, I hope everyone's having a great weekend, great day, and all this stuff. Man, these days go by fast. I need to kind of do more of my days. But all right, let's get to it, shall we? All right, so let's say we have or given, I don't know why I'm reading it like this. Given a weighted undirected connected graph of n vertices from 0 to n minus 1, what does this 1 1 mean? I and weight. Oh, because it's an edgeless. I see. It's a weird way of phrasing it, but I guess is it because you can have the same? Oh no, it's distinct. It's a really weird way of drawing it, maybe. Like the edges are. Oh, I don't know. Yeah, maybe it's fine. All right, so find the critical and pseudo-critical edges in a given graph. What's a critical graph? Okay, an MST whose deletion from the graph would cause the MST rate to increase is called a critical graph. On the other hand, a pseudo-critical edge is that which can appear in some MSTs but not at all. Note that you can return the indexes of the edges in any order. Okay. I guess the index is used for returning, which, okay, that's fine. Wait, is it? What? Oh, yeah, okay. No, the input is fine. I think this drawing is... Okay, I guess that makes sense in the context of the output. Okay, alright, let me reread this. Okay, so critical edge is okay, so that means that I think the first thing I would try to do is kind of rephrase the problems in a way that I can understand it. And to be honest, right now I'm not, MST, minimum spanning tree, is something that comes up a bit in algorithmic courses, but to be honest, like they come up here and there, but not super often. Even on Leetcode, right, or competitive, but they do come up enough that it is one of the fundamental things that people, I think the reason why it just doesn't come up that much is not because it's not as interesting or critical as other things, as other things, but it's just that there are not that many variations on things you can ask about an MST, a minimum spanning tree. Like maybe, and I don't know if this is true, but this is just a hypothesis. It's just that there are not that many variations of the prompts that you can ask, is maybe what I would say. But that aside, I think it's just me trying to say that, like, it's still important-ish to know at some point, or it is on some level, but it doesn't come up super often, relatively. But the thing about MST, I would say, is that it is one of those canonical greedy problems in which, it is one of those things that you can build greedy not explanation, but greedy proofs from. So definitely is one of those things that is good to learn, if to just kind of get yourself into understanding why greedy is greedy, especially when you're starting out. Okay, that being said, okay, so what happened? So what is a critical edge, right? So a critical edge is when you remove it, the MST increase, and that only happens when. Is that true? Let me think about this. I was going to say something, but I have to make sure that it is true. When you remove an edge, sorry. So given an MST, if you remove that edge, the MST rate increases, right? So let's say you already calculated the MST, and then you remove it. How do you replace? Then the only way that it doesn't improve, if you will, or not that it improves, because it can't improve by definition of MST. You already have the optimal tree. So the only way it doesn't increase, so it stays the same, is if I think I have to draw stuff here. I think I've been trying to use a lot of vocabulary. So give me a second. Let me take out my drawing pad. And let me make sure I put it on screen. I don't know if y'all know this, but when I'm at home and not traveling, I have like one of these drawing things. Still don't make good use of them, but you know, at least I'm trying. Yeah, okay. So I think the idea here is that, okay, right? You know, let's say we have some, you know, nodes in MST, right? And it's gonna look something like, you know, whatever, right? You know, I'm just gonna draw about it. So, right? Right? Let's say this is the MST, and let's say this is the node that you're caring about, right? Actually, let me change my mind. Let's say this is the node that you're caring about, right? And that's a node that has multiple things. So let's say you remove, you don't care about the node, you care about the edge. Man, I'm really not explaining this well. But let's say you're looking at this edge, right? So what happens when you remove this edge? Well, when you remove this edge, that means that now you have two connected components that are disconnected from each other that used to be together, right? So that means that now the only way that this is a critical edge if there does not exist an edge where, you know, like it connects the two connects. English is hard. Connects the two components, because you have this component now, and then you have this component now, right? Oops, I missed Mr. Dupu. So. And then now that you have to try to find another edge that is either the same weight. If it's the same weight, then it is not critical. And if it is, if you cannot find one of the same weight, then what was the other one again? Pseudo-Critical. All the edges either. Yeah. I just focus on critical for now. So that's the case, right? So okay. So that's basically the idea that I'm thinking about, but I have to think. Okay, so that's like a concept, right? But I don't know what to do with this yet. Is what I'm saying. Because you can. Actually, let me take a look at n. Always look at the constraints. Okay, n is actually only 100, and actually only the 200 edges. That frees me up a little bit more, because to be honest, I was constraining myself to linear solutions. But of V solutions, or you know, something like this. But now we can definitely be a little bit more loose, because n is only 100, right? We can even have n cube solutions if we can. The other thing is rate is less than 1,000. I don't know if that helps, but and edges is only 200. So even if I don't know. We have to figure out how to put all these things together. But these are good observations, and that allow us to be more brute force than that. I mean, that's not to say pure naive brute force, but allow us to be a little bit, you know. Yeah, because now we can say, well, I mean, in theory, even we can actually even calculate the edge, right? Because we calculate. So okay, so. Let's say let me just calculate what is the most brute force thing we can do, right? The most brute force thing that we can do is that, you know, we have y edges, oops, caps lock, y edges, right? And then for each edge, calculate new MST. Would that be fast enough? Well, this one is all of y iterations, and calculate new MST lazily, you know, we can do y log y, which is going to be fast enough, right? Because this is just at most y square log y, and I'm just using Cusco. I mean, you know, you could also do prims, which is prim's V square? I forget. Yeah, I guess so. I guess prim is, no, let's see, for each one, you update and then you get the min. So that's V square, right? So it's either or V square for prims. U log E is from sorting the edges from Cusco. Cusco? I don't know. Cusco? But in either case, right, this is going to be V log times C. This is, of course, up to at most 200. So that's, 40,000 times log for 200, which is what, which is less than 10, right? Because 2 to the 10 is 1,000. I know it's 1024, but it's roughly 1,000. So yeah, so this is less than 10, so that should be even fast enough. Just back of the envelope, right? Yeah, and this is times 100, which is actually a little bit slower, but still fast-ish. Oh no, I did E square. So this is actually So I mean, it's not fast, but it's not slow. Like this would probably be good enough if we just did naive for the critical. And that's how I would think. And yeah, I kind of missed, or I did not read I'm a little bit slow there. I didn't read the constraints early enough. So I think I would do this for the critical edge. What is the because that is easy to do. But let's see what is a pseudo-critical edge. Let me reread it now that I think I have at least something knowing the constraints, right? A pseudo-critical edge is which it can appear in some MST but not all. What does that mean? That's phrasing. I mean, it just means that if you remove the edge, it does not change the MST, right? Yeah, I mean, I think that's it. But the problem, I think in theory we have to do this twice, maybe, or at least if you're doing it lazily. Because basically we have to see if this edge is in the MST, and the problem with trying to and this one, I don't know if you can do it. I think the naive. My first thought, and I don't know if it's that naive, is to calculate the MST, and then for each edge in the MST, which now reduce this O of D thing to O of V thing. But that's not always true, right? Because this MST doesn't have to be unique, right? And because this thing doesn't have to be unique, I don't know how to, versus just for each edge. I mean, this is still fast enough, but it is not as fast as I would like, I suppose, right? Basically, we're calculating 2 MSTs for each edge and 1 MST, so that's like, yeah, that's a lot of MSTs. We could save time on the sorting, but that doesn't change anything really. Is that gonna be fast? I think I'm still trying to think a little bit whether that is fast enough. Yeah, I mean, okay, let's give it a go. I think the math makes sense. I don't know if there's like a slicker algorithm, at least off my head. If we need it, we need it, and then we'll see if we can optimize some parts of it. But for now, we'll just do it that way then. Yeah. Okay, so I'm gonna try to use. I'm not gonna go over all the what I was going to say. I'm not going to go over the minimum spanning tree algorithm, though it is, like I said, a very good algorithm to kind of read up and make sure you really understand. But at the core of it is greedy, and I don't know that I would say I remember it, other than remembering that it's greedy. And because of that, because because I do know that it's greedy, the implementation is actually very straightforward to rederive, right? Like I don't memorize templates or code or whatever. It's just that I know the thing to know is just that you sort out the edges by the weights and then just go add them one by one until you have a full graph. Okay, so yeah. Let's just say we have a MST algorithm. What am I doing for this MST? I'm trying to figure out how to generalize these things in a good way without like creating the entire graph again. Obviously, this is why I'm trying to think in it a little bit. But clearly, you know, we have to do it in some ways. So basically, okay, so we have to, let's just say we have some index for the edge. And then we have to calculate two MSTs, one assuming that this edge is in MST, and then calculate it, and then calculate, and if that's true, then calculate whether the new, and then calculate the MST without it, right? So this one, I guess we can do something like use a code word, whatever, keyword. Yeah, okay. Basically, we always skip index, and then we just see if we start with using this, right? So, okay, so maybe I'll just code start then. Okay. Okay, and this assumes that we already sorted the edges, because I guess we have to go in this case anyway. Okay, yeah. Let me just remove this so I could have more real estate. What am I doing again? Okay. Oh yeah, sorting. So yeah, let's just say the edges, you go to sorted. We have to keep track of the index, right? Because that's what we're returning. Okay, yeah. We want to enumerate edges. So we want to sort this by, what are we sorting by? We want to sort it by, what is the weight? Weight is the third thing. But this is now, so it's x of 1 of 3 maybe? Yeah, or 2, whoops. 1 because of the enumerate, so that we get the index in this as well. So yeah, okay. And here we do, you know, for Kushko, we do need whatchamacallit. What do we need? We need union find is what I was going to say. Man, I'm a little bit slow and off today. But yeah, also I'm not going to go over union find, but I actually, okay, fine. Yeah. I guess I'll put this in a class to make it slightly easier. So we have n items, right? So parents, you got to x for x in range of n to the n plus 1. Should be okay. And then we have find and this is just standard union find things. I'm not gonna go over it in this video because I don't know, that could be a big thing in itself. So but yeah. Right. And then okay, so then now we have we have n items, right? Let's make this big N. All right, and then if start, so if this is true, then we add and what do we do? Then start u, start we, start weight, I suppose, is equal to edges sub index, and then you find dot union su sv. That's the total weight. We assume that they're not connected because this is the first edge, right? Otherwise. So we always skip index because either we use it at the start or we don't use it at all. So then here for index UVW in edges, right? If this index is terrible, but current index maybe that's slightly better. I don't know. Naming things is hard, right? If index is equal to current index, then we continue, we skip this no matter what. Otherwise, if f dot find of u is not equal to uf dot find and of we union them. And I guess we can also early terminate, but should we early terminate? Let's do it. If count is equal to n minus 1, then we break, and then we just return total. I think this is roughly right from MST, and is it union find, and yeah, okay. Now we just have to do it for every edge as we said. So yeah, for I should have a big E, I suppose. E is a good length of edges. So for I in range of E, yeah, I think what do I need first actually? I need to do the standard minimum spanning tree. So let's just say base MST is equal to MST of current index to the true and force. We're not skipping anything, should be fine. Or we don't start with and we don't skip anything. I think that should be fine. Hopefully it is. Because if it's not, that'll be a little bit sad. Otherwise, yeah. So if MST of I, let's say we start this. If this is equal to base MST, that means that this edge is part of at least one MST, then it is at least pseudo-critical. If MST of I force is not equal to base MST, then this is critical, right? let's actually also put the answer. So critical is equal to pseudo-critical is equal to. So if this is not, that means that this is critical. And then we can append I. If it is the same, then it is pseudo-critical because it's apparently yeah, it doesn't have to be in the thing. And I think that's it. I think that's it, maybe. At least my understanding of it, hopefully. Is that true? Oh, this is ye, not edges. I make that mistake actually common, so that's a little bit unfortunate. Oh yeah, I always call it you fine, because sometimes I do it in line. Okay. Am I confident about this enough to submit? I mean, because that was the first test other than, I guess I have some, typo about the name. But, so is that good enough for me to submit? Alright, let's just YOLO. Let's see. Yeah, that was good. Very slow. What did I do 3 years ago? That was fast. I got a wrong answer. Was that during the contest? Probably. Yeah. Oh, I did it another way last time. Maybe. Well, yeah. Wow. I mean, I did it much faster that time. I mean, this is good. It is very slow. Oh no, it's still 60%, but apparently I did it like really ridiculously last time. But yeah, the complexity. Let me just go over this complexity first, and then maybe I'll take a look at my previous code. As we said, this is the algorithm that we did. So, and we did the ye log ye one. So this is going to be O of ye. Yeah, for each ye, we do another ye log ye. So ye square log ye. Keeping in mind that ye is constrained in this way, and that is your time. Of course, space is going to be O of ye for a copy of the sorted array, and yeah, a copy of the sorted array, a lot of union find stuff, which is linear on n. So this is actually v plus e or what n plus e or whatever space at least. I guess that technically, if you want to be precise, that's the time because you have to look for the time. I mean, this is all of v no matter what because you have to at least spend the time to allocate the space, right? But I think the thing that I noticed last time, and I did notice this here, was that the rates are up to 1,000. But I didn't really, I didn't get to the point where I was thinking about it. But it seems like here in the past I did do something like this. What is get psycho? Man, it seems like I'm doing some really complicated things here. There is something about union find. So I don't remember what I did here. My guess is that we're doing Cusco all together. Based on the weight, because, and this is just like a counting sort. I don't know why I did it this way, but it's fine maybe. Yeah, I mean, this is just a counting sort. This is a weird way of putting it, but it seems like I did do something smarter, because you can think about this as O of ye anyway in terms of O of edge, and I don't know. What does get psychos do? Past Larry has some funky, crazy things. Oh. This is I mean, this is psycho counting back edges. I guess the idea here is that man, what is Past Larry is ridiculous, but okay. So basically, this means that the minimum spanning tree changed, and when we're done, then we'd have to consider all the edges. And basically, the idea here is that when you process all the edges at the same time, or all the edges of the same weight at the same time, then the thing is, okay, you every step of the way, you try to figure out altogether whether that causes a new MST, and if a new MST emerges now, then what that means is that all the edges together, but there are only two kinds, right? That means that all the edges that we process this step are important in that those edges are the step, or those edges are the edges that are in the answer, right? And those edges, are either critical or pseudo-critical, because in those cases, yeah, in those cases, they're either critical or pseudo-critical, because by definition, it means that all the that is an interesting observation, is that all the critical and pseudo-critical edges all have the same weight, because there's only one instance in one instant in time in which everything becomes connected, and then there are only a couple of cases, I guess. Man, past Larry, current Larry is not as smart, maybe, but. Okay, so and these variable names. Oh, these are the edge weights of the current edge rate, right? What is P? Oh, I think I just keep. Oh, I see. Wow, this past Larry is writing some really dubious looking code. But basically, what he was doing is he's keeping track of two trees, and then basically just checking to see if this is done. If this is done, then it's just looking up on the previous tree and whether this edge was processed, or this edge created was needed, because this is the previous tree, and then we're doing comparisons, and if they're not the same, then we just have to consider them, and then for these edges we try to determine if there's a cycle in just those edges, and then which determines all these things. Do the cycles things matter? I don't even know what I do here. I guess I do. Let's see. Get cycles. Oh, I see. Yeah. So basically, we're looking at the back edges and seeing whether if there's if there's a back edge, we should consider it. Wow. But basically, it just gets all the edges that are part of a cycle. Also ridiculous code. Don't know if I can write it today. Yeah. So if it is part of a cycle, then it has to exist because they all, I don't know. I don't know if I understand this one. Past Larry is ridiculous. This is actually ridiculous code. Let's take a look at editorial then. I mean, this is basically what I did, right? Yeah, this is what I did, I guess. Wait, why is it only v square? Did I mess up? Did I misread this? Oh, I wrote y log y here. I am wrong on the complexity. My bad. Because this is all of, this is actually now all of y. Because we already did the sorting. That's why. Oh yeah, man. I think I was just focused on the other thing and I got distracted. My fault, friends. But yeah, because we already did the sorting, so for you, so we can do all this. So yeah, so this is all of y, not v. I mean, I guess v squared is technically also true, but we, because of this is actually only y squared. I mean, technically, plus y log y if you want to add it back in for the sorting, for initial sorting, but we don't have to sort every time we remove an edge, just, which is why you're able to get rid of it. I forgot about that, actually. Whoops. Yeah, I mean, they don't even go over my other solution, I suppose, which is because it's ridiculously complicated in the way that I did it. Yeah, everyone seems to do it that way, and not with the cycle calculating way. I'm gonna go watch my old video and see what I did here, because this is actually, I mean, and you can see that. I mean, you can see that this is much faster. I don't know if it's still true or just like a sample case thing, but I mean, the reason why it is faster is just because it doesn't have. I mean, there is the sorting on the edges, kind of. Yeah, I guess it's actually strictly, well, not strictly, but it's probably on average faster than the sorting. But basically, we're doing all the weights together, and everything is like the cycle finding is linear. So that means that this is y and this is v times y at most versus y squared, which maybe for certain inputs is much better. I don't know. Anyway, that's all I have for today. Let me know what you think. I have to go for a jog and then food. So yeah, stay good, stay healthy, to good mental health. I'll see y'all later and take care. Bye bye.